In our last lesson, we started exploring the idea of exponents. In this lesson, we're going to see how we can work with exponents a bit more efficiently by discovering some exponent rules. Now, rather than jumping directly into saying what the rules are, we're going to look at some examples first which illustrate how these rules work so we can understand what they're doing. So if we have an expression 3 to the power of 5 times 3 to the power of 2, we can write this out in expanded form. But notice that because both expressions have the same base, namely 3, we can write this all out with a single exponent. It's 3 to the power of 7. Notice that what we've done effectively is just add our two exponents, 5 and 2. If we have 5 to the power of 9 divided by 5 to the power of 3, we can also write this out in expanded form. And because multiplication and division are inverse operations, we can eliminate some of our 5s, and we're left with just 6 of them. So this is 5 to the power of 6. Again, notice that because we have the same base, we in effect just subtracted our exponents. So the exponent product rule says that multiplying expressions with the same base is equivalent to adding the exponents. And the exponent quotient rule says that dividing expressions with the same base is equivalent to subtracting the exponents. Let's look at a few more examples, but this time we're not going to write them out in expanded form. We're going to use our new rules to quickly and efficiently simplify them. So 2 to the power of 8 times 2 to the power of 3, same base, which means we can add the exponents, which is 11. 7 to the power of 6 times 7 to the power of 13, same base, so we can add the exponents to get 7 to the power of 19. X to the power of 5 times x to the power of 9. We have a variable instead of a number for our base, but it's still the same base, so it's x to the power of 14. 6 to the power of 14 divided by 6 to the power of 5. It's the same base, but we're dividing, so we can use the exponent quotient rule to get 6 to the power of 9. 4 to the power of 3 divided by 4 to the power of 8 is 4 to the power of negative 5. And t to the power of 10 divided by t to the power of 7 is t to the power of 3. Suppose we have a situation that after applying an exponent, another exponent is applied, such as 2 to the power of 3, which is to the power of 4. Well, in expanded form, 2 to the power of 3 is our base, so we have 2 to the power of 3 multiplied 4 times. But each of those is an exponent which can be written in expanded form, which looks like this. What we have now is 4 groups of 3 lots of 2 being multiplied. In total, we have 3 times 4 2's being multiplied, which is 12. So this is 2 to the power of 12. Now we already saw in the last lesson how we can expand expressions with a negative exponent. But notice our denominator when we do that is just a series of our base being multiplied. So we can write that as a single positive exponent. So a to the power of negative 5 is the same as 1 divided by a to the power of 5. These give us our two next rules. The exponent power rule says that raising a base to a power, then another power, is equivalent to multiplying the exponents. And the negative exponent rule says that changing the sign of an exponent is equivalent to taking the reciprocal of an expression. Remember that dividing 1 by a number is equivalent to its reciprocal. So we can simplify these examples where we have a base to an exponent, which is then to another exponent. So 3 to the power of 4 to the power of 2 is 3 to the power of 8. 10 to the power of 5 to the power of 3 is 10 to the power of 15. And b to the power of 7 to the power of 6 is b to the power of 42. Each time we're just multiplying the exponents. If we have 5 to the power of negative 7, using our negative exponent rule, we can write this with a positive exponent as 1 divided by 5 to the power of 7. Sometimes we want to do this the other way. So if we have 1 divided by e to the power of 11, that's the same as e to the power of negative 11. Now on top of these rules, there's a couple of special values for exponents that we want to make note of. Now you may have already noticed these in the last lesson. If we have any exponential expression with 0 for the exponent, as long as the base is not 0, that expression is equal to 1. And any exponential expression with 1 for the exponent is equal to the base. So here's some more complicated examples that we can simplify by using multiple rules. But we're going to take them one step at a time so we keep track of what we're doing. So t to the power of 8 divided by t to the power of 11 is t to the power of negative 3 using rule 2. Now if that's then multiplied by t to the power of 5, rule 1 lets us add those exponents to get t to the power of 2. If we have s to the power of 4, which is then to the power of 7, rule 3 lets us multiply those exponents to get s to the power of 28. Now if that's multiplied by s to the power of 5, rule 1 lets us add our exponents, and we get s to the power of 33. If we have a to the power of 2 to the power of 3, rule 3 lets us multiply our exponents to get a to the power of 6. If that's then divided by a to the power of 13, rule 2 lets us subtract to get a to the power of negative 7. And if we want to write it with a positive exponent, rule 4 lets us write it as 1 over a to the power of 7. If we have b to the power of 2 times b to the power of 4, rule 1 lets us write that as b to the power of 6. If that's then raised to the power of 3, rule 3 lets us write that as b to the power of 18. And if that is being divided under b to the power of 22, rule 2 lets us write that as b to the power of 4. Now all of the rules we've worked with so far assume we only have the one base. That's not always the case though. But as long as we have expressions that are being multiplied or divided, we can work with expressions with different bases as long as we keep those different bases separate. So if we have a to the power of 3 times b to the power of 5 times a to the power of 7 times b, let's start just looking at the base of a. 3 plus 7 is 10, so we have a to the power of 10. 5 plus 1 is 6, so we have b to the power of 6. Remember, anytime we have a base without an exponent, there's an implicit 1 for our exponent. If we have x to the power of 5 times y to the power of 2 over x to the power of 4 times y to the power of 8, by dividing our x factors, we get x to the power of 1, which we can just write as x, and we get y to the power of negative 6. If we have s to the power of 4 times t to the power of 5 times s to the power of 2, we can multiply the factors with the base of s to get s to the power of 6. If that's then divided by t to the power of 2, we can subtract our exponents for t to get t to the power of 3.